Okay, so hello everyone. So my name is Leonardo Banchi. So my email address is the one written there. I'm from the University of Florence, so I'm kind of a local guy here. So today, we will do the second lesson of variational quantum algorithms. So yesterday you had the first one with Peter, and so today we will continue along those lines. So I will start very slowly with some blah blah, just to wait for a few more people that are coming perhaps from I'm going uphill now, and then I will present a bit some more technical stuff. So the topics I will cover today are basically the following. So I will say something more about the optimization of variational quantum states for different problems like VQE. So all the applications you have seen yesterday, and yesterday you have also seen how to use how to compute gradients on a quantum computer using the parameter shift rule, which is nonetheless limited to some specific gates. So here I will, let's say, introduce some more general versions of it that can be used, for instance, also when you don't have qubits, when, for instance, you're Hamiltonian. So you are differentiating over parameters of a Hamiltonian and different physical evolution. And nonetheless, it can also be applied when you don't have qubits, but you have, let's say, more general objects or like representations of different groups, which might be useful for people doing field theory. So that's the first topic. So the first topic would be about gradients. So using gradients, so the good point about gradients is that they allow you to do some theory. And so, for instance, one can prove, let's say, one can find some theorems that tells you basically what's the difficulty of finding the optimum. So for how long does your algorithm have to run? And so, here I will introduce some aspects about how to define let's say, the trainability, so how we can optimize this variational circuit, and how is that linked with expressibility. So more, let's say, expressible circuits, you will see that they are more difficult to optimize. So something related to this is the problem of Barren Plateau. Which is basically what happens when, I will show you that basically what happens is that when the circuits become very deep, or you have many qubits, then what happens is that the cost function landscapes becomes almost flat. So gradients are very small, and so the optimization becomes very slow. So, and on the last part, I will study some applications. So you have already seen yesterday applications with Peter to use VQE, so for estimating ground states. So today I will show also other applications for simulating dynamics, but also for finding low energy theories like Schrieffer-Wolff approximations on a quantum computer. Okay, so this is more or less the outline of this lecture. And as I said, I will start very slowly with some blah blah, also to allow people, more people to come. So, so what are these variational quantum algorithms? So, if you have read quantum computing textbooks like Nielsen and Chuang, and then you look at the algorithms that have been developed for NISQ devices, so these Noid intermediate scales quantum devices that are available nowadays, so you realize that they are kind of quite different. And so the reason is that, so when you read Nielsen and Chuang, so it is assumed that one is able to find perfect gates, for instance, by error correction, and to have also as many qubits as you want. So in books like Nielsen and Chuang, so everything is written in a quantum language, since basically all the classical computation can be done also in a quantum computer with basically polynomial overhead, so little overhead. And one is interested in asymptotics, so whether things scale exponentially or polynomial in the number of qubits, and one, of course, wants to prove some quantum advantage. So on NISQ devices, so what's the kind of quantum computers we have now and that are likely to be available in the next years, you have noisy gates. And so that what happens is that you have wrong outcomes, and you need error mitigation strategies that you will see also, I think, tomorrow. And the problem is that quantum resources are very limited. And so we need to use the quantum computer only for the hard part of the calculation. And everything that can be done classically should be done classically. Okay, so that's why people have developed different hybrid methods where classical and quantum resources are used sequentially to achieve a certain result. And the structure of these hybrid methods is the one that you have also seen yesterday. So normally you assume that you have like a quantum register that you initialized into some reference state, which is normally 0. Okay, so this state is made with several qubits. And then on this register, you apply some quantum operation, like unitary gates. And then at the end, you take some measurements. And then somehow, based on the outcome of these measurements, so you send a classical device, processes the outcome of these measurements. So this is like the classical part of the algorithm. And then somehow uses this partial knowledge somehow to reprogram the quantum machine, and so define a new circuit. So we are using this kind of feedback loop, where somehow the outcome of the classical computation are sent back in order to find new parameters here. So as an example, I mean, you have seen yesterday gradient descent. So one can use the quantum device to compute gradients of a cost function like a Hamiltonian, so the energy of a state. And then one can use the classical device in order to update the gradient. Now, let's consider some example now. So the crucial aspect is that what we can do in Q, which is the quantum part. So as shown in the Davide's lecture, so the first lecture, the unitary operations are done by basically performing some time evolution with a driven Hamiltonian. So something which is written like this. So you have some time order exponential of 0 time with some Hamiltonian. So that's how the quantum gates are physically implemented. And so different systems have different Hamiltonians, and so different evolutions, but in general, by sending suitable control pulses, or so one can find different use, and one can build, let's say, some elementary building blocks like single qubit rotations, like this, where sigma, alpha. So I'll try to use the hat, because here we are mixing classical variables and operators. So I'll try to use the hat to denote operator, but most of the time I won't remember. So sorry for that. So this sigma alpha are the Pauli operators. So these rotations can be basically done in most of the quantum computing platforms available nowadays. And then there are some interactions between qubits, like the swap gates, C0, and you can build arbitrary circuits using these building blocks, as you have seen yesterday. So so typically, once you have this and once you have these gates, so you can build a generic state, psi of theta. So psi of theta, so this Q part depends on some parameter theta, classical. And so psi of theta is the state you get here, before the measurement, sorry. So psi of theta normally can be written as a product of layers, where you have some layer U that depends on theta. Then you have some unitary, which is independent on theta. And you apply, let's say, a sequential set of this set of unitaries, starting from the state 0 that we did. So as you can see, so here we can decompose the unitaries as something that depends parametrically on some external parameters, like for instance, the duration of the pulse, or something that you can you can tune in experiments, and something which is independent. So here L is basically the number of layers. So I'll use this name here, and while the W are independent on the parameters, and U, J might depend on, let's say, all the parameters. So theta for me is like a vector of parameters. So theta 1, let's say, up to theta m. So this is a vector, okay, not just a single parameter. So normally, when you're interested, when you read quantum computing textbooks, so you have to you normally find a discrete set of universal operations like Hadamard, C0, and so forth. But here, on the other hand, we are using also this continuous degree of freedom. And why? Well, simply because we can. So in these devices, one can apply these parametric gates kind of for free, because we can basically change the pulse duration and so change this parameter theta. So although, I mean, you might know that any gate can be approximated with a certain precision with a discrete set. That's also the Solovay-Kitaev theorem. So it is much more efficient to exploit this continuous degree of freedom, since it's basically there. And since the number of operations in these devices is very limited, so we should also use the most of what they offer, and so we should exploit this continuous degree of freedom. Now, so this kind of object here is called by people either parametric quantum circuit, but some people also call it kind of quantum neural network. I mean, quantum neural network are a little bit more general because they also depend on some external parameters. And so, so the reason why they're also called quantum neural networks is because they share similar properties to the neural network. So, for instance, they can be universal in the limit of when we have many parameters. Of course, we won't get into that limit with current computers. And also, this is also true if the hardware allows for, let's say, a universal set of operations. And moreover, also another similarity is that they can be trained with gradient descent. Now, so now that we have like a parametric quantum state, we can use it to find variational approximations of, for instance, of the ground state, or use it for any other, let's say, variational approach that have been developed in quantum mechanics. So the typical starting point of variational methods is the introduction of a cost function. So cost functions, I mean, typically they can be written like this, or in some similar fashion, where A here is an operator, and psi theta is our variational state. So for instance, so when A is the Hamiltonian, then basically the cost is the energy of the variational state. And so minimizing the cost is like finding the variational approximation of the ground state, and this is exactly the BQE. But this different cost function can be introduced for different problems, but most of them can be somehow rephrased in this language. So in the hybrid quantum algorithm, so this works by using a quantum computer to estimate the cost. And so if the state basically uses n qubits, so its classical simulation would require an exponential amount of resources, while somehow on a quantum computer, so this is done kind of for free. So the point is now, how do we do this optimization? And you have seen yesterday that one can use gradient descent. And because this has many theoretical properties, but let's try to somehow rephrase that a bit and study that a bit more, how we can use gradient descent. So in general, so when you do numerics on your computer, so the starting point for using gradients is to use a finite difference approximation. So one can write d c d theta I as approximately as c theta plus epsilon ei minus c theta divided by epsilon, where this vector ei is something which is 0, 0, then 1, 0, where the 1 is on the ith position. But the problem with finite difference is that you may need to evaluate the function f, the function c, with an error which is much lower than epsilon, which is already small. Indeed, let's try to understand this point a bit more. So let's assume, for instance, that A can be written in the diagonal form, like this. Now, for just one moment, let's suppose that one can do measurements in this basis. I mean, of course, this is normally not possible, but let's assume for the moment that you can do measurements in this basis. So for using the Barren rule, measuring A, so means that basically all the times you get some results AL with probability, which is given by the Barren rule. So AL given theta, which is given by psi theta AL square. So if now you take M measurements, so what you do is that somehow you approximate your C theta as 1 over M, so which is basically the number of measurements, so the number of shots. So sum L between 1 to M of A, O, L, and this is, let's say, this is the outcome L. Now, this is an approximation, of course, of the exact expectation value, which would be, on the other hand, this the expectation value of A with respect to theta. And the variance is, of course, somehow A theta square minus A theta square divided by M, which can be small. So this delta, I mean, in principle, we should choose M to make this small. But let's see what happens if we don't make this M, if we don't make this very small. So for instance, suppose that this is our function. Okay, so, and we are somehow interested, so this is theta, and this is, let's say, theta plus epsilon. So theta is here. So let's say the true gradient would be this one. Right? Now, the finite difference approximation is still bad, but at least it goes into the right direction, which is this one. But because somehow now our cost function, we don't know the exact value of the cost function, so we know that only up to some error bars. So let's put some error bars, even some large ones, just to, I mean, you won't have this this error bar, right? But just to make the point. So suppose you have this error bar, so it means that somehow you can get any point here with some precision. So if you try to do the finite difference approximation with this error bar here, then you see that the gradient somehow is this one here, right? Pretty bad. Now, of course, I mean, you won't do this, but so this is just to say that somehow because this epsilon is very small. So because this epsilon is very small, so basically you need that this delta, which is somehow the size of the error bar, has to be much smaller than the epsilon. So delta is the size of the error bar, epsilon is the precision. But epsilon is a small number. Otherwise, I mean, you're making an error like in this red part, which is the finite difference. Okay, so you have to choose epsilon small to avoid this kind of error, but then you have also to choose delta much smaller, and that's challenging. So that's why you need strategies where somehow you measure the gradient directly on the hardware in order to avoid this sort of problem. Now, remember that I was cheating a bit because I told you that somehow this A is written in the energy basis, but we don't know the energy basis, right? I mean, otherwise the problem becomes trivial because in VQE, I mean, we are interested in the ground state. So if you already know this decomposition, then everything is done. So I was cheating somehow, but basically what I just said happens in general, because what you do in general is somehow to write A. For instance, suppose that you have a Hamiltonian, you can write the Hamiltonian in terms of Pauli strings, so product of Pauli operators. So this PL for me is a product of Pauli strings. So for instance, a Hamiltonian can be written, so this is, I mean, usual Ising model, for instance, Ij sigma Ix sigma Jx plus some fields. Okay, so this J are the coefficients lambda and also the H, which are the external fields. And somehow everything can be written in terms of product of Paulis. So you don't measure directly the energy. So what you do in the measurement is that you measure the Pauli strings, and then from that you estimate the energy. So basically what you do is that somehow you use this trivial decomposition. Okay. So basically what I just said about the error bar applies also in this case. Simply you don't measure A, you measure this Pauli strings, and then from that you reconstruct the energy and the variance. Right, so the take-home message here is that we need many shots to have a very good estimate of the gradient. And so the way to measure, so we have basically to find the strategies to measure the gradient directly on the hardware. So yesterday with Peter, you have seen that if you can somehow isolate the dependence on theta, something like this. So let's suppose that somehow we are isolating the dependence on theta j here. So, and the assumption here is that this W, so these are independent on theta j, but possibly dependent on theta I with I different than j. Okay, so we are trying to isolate this theta. So it's a little bit more general than that, but somehow I'm saying that if theta, if x square, so this operator satisfies this identity, then you have seen yesterday with that basically the derivative of C with respect to theta j can be written as C theta plus U by 2 Ej minus C theta minus U by 2 Ej divided by sinus of U. Okay, so I won't rederive this because you have seen that yesterday. But so you realize that here we get something which is kind of a finite difference approach, but this one is exact. And so we don't have to somehow to make error bars very small because it's much smaller than epsilon, simply because we have no epsilon here. So everything is exact. And all of this costs here, so they can be estimated by measuring A as before, simply with a different circuits. So the complexity is that we somehow have to use two different circuits. So two different circuits. With basically to estimate this quantity. So suppose that somehow, let's call, so we have to measure this A operator, or somehow any Pauli string decomposition of it 2 times. So let's call A plus minus O S J, so many indices. So the outcome of shot S, so parameter J, and then plus minus means that basically we are either considering theta plus minus U by 2 Pj. Okay. So the way you do the way you estimate this gradient when you do the measurements on the hardware is that you write the derivative of C with respect to theta J as 1 over m sum S between 0 and m. M is the total number of measurement shots. So A O S J plus minus A O S J minus divided by sine U. Okay. So I'm saying that explicitly because just I want to introduce this quantity. So let me introduce this this random variable GI, which is A O I J plus minus A O I J minus divided by sinus of U. So we can say that somehow because of this derivation, actually not my derivation, so you have seen the derivation yesterday. So because of this derivation, so G is an unbiased, in the language of statistics, is an unbiased estimator of the gradient. So what does it mean? So it means that basically if we take an infinite number of measurement shots, then you get the exact expectation value. So in statistics, so it means that basically derivative of C with respect to theta J can be written as an expectation value of this GE, where this symbol here means expectation value, the empirical expectation value with respect to the number of measurement shots. And I mean, now that you have this, this decomposition here, it's now also trivial to realize that basically the variance of this estimator is basically proportional to sinus of U minus 2, simply because sinus of U is here on the denominator. And so the optimal choice for this parameter U, so this parameter shift rule works for any possible U, but the optimal choice of this U is the one that actually minimizes the variance, and so maximizes the sinus. And so the optimal choice is for U equal to pi by 2, okay, which is the one that you normally find in the literature. So now that somehow we know how to measure the gradient of our cost function, we can use a classical computer to update the parameters, for instance, by gradient descent. And I will tell you something more later about this. So here, I just want to also briefly mention that one can keep the number of measurement shots constant, but one can also adapt the number of measurement shots at different iteration. So adaptive So if you're interested in these adaptive strategies, which are a bit more involved numerically, but not that much, so you can find the code in this paper here, which is by Kubler, and it's on arXiv. So this is et al., which is 1909.09003. Right. I have to say that somehow the main reference of this lecture is this paper here by Cerezo and others. Yes. Yeah, I will go back. The sign U, this U. It's a U, yeah, I mean, bad handwriting. That's my problem. I mean, that's also why I use a tablet, because if I use, I mean, I like blackboards, but in blackboards, my handwriting gets exponentially smaller as a function of the characters. And so, I mean, tablet is better normally. But yeah, sorry. The question was, so sign you, yeah. Okay, so if it wasn't there, I mean, perhaps you already found the one with pi by 2. I don't remember exactly, but it's so the shift rule is more general. So it's true for any possible u like this. So perhaps in the yesterday derivation here there was already some pi over 4 or pi over 2 depending on the gate, but the derivation is exactly the same. It's a bit more involved, but not that much. Yeah. Right. Yeah. Other questions? Right. Okay. Okay. So this somehow is something that you have already seen yesterday. So let's try to do also something a bit different, because so this parameter shift rule only applies if you have gates like this. Okay. Now these are very common gates because all the single qubit rotations can be written in this language, but somehow they are not the most general ones. And for example, if you have like a machine which is doing analog computation, or if you are working more close to the closer to the hardware, then somehow you might get some gates which depend on parameters like this. Okay, so you have like a time evolving operation for some Hamiltonian, and the tunable part in your experiment is, for instance, a magnetic field or some other external parameter which is inside of the Hamiltonian. So, I mean, this is not some, let's say, abstract, let's say, academic question, simply because some also native gates that are in some computers look like this. So, for instance, the cross-resonance gate, which is used in IBM, which is the native gates in several IBM quantum devices, normally can be written like this. Or, for instance, if you also have like an analog device where what you're doing is that, so the computer is actually performing an evolution with respect to some interacting Hamiltonian, like, again, the usual Ising. And the theta is basically the external field in, for instance, over Z here. So again, you cannot use this parameter shift rule to find gradients if somehow your parameters are here. But however, in this paper, which is so here in archive 2.5.10299. So we have shown that somehow how to take gradients also with respect to parameters of any general multi-qubit gates, so like the one shown here. So without loss of generality, so one can write these gates as an exponential of some I Hj, which is a Hamiltonian, plus theta j Vj. And once you do this decomposition, then somehow the trick was to use an identity from operator theory, which is this one here. So this identity is an identity from the algebra theory, basically, that tells you that whenever you have the derivative of an exponential of an operator z, you can write this derivative as an integral with respect to something else. Has anyone seen this identity? Yes, it's a pretty common one, right? So using this identity, and now you say, okay, so this is an identity, so we are just turning a derivative into an integral, so it looks more complicated. But actually, that's not the case, because if now you apply this identity to this cost function here, then somehow you realize that, so the derivative of c with respect to theta can be written as an integral over ds of a function that we call it c plus theta s minus c minus theta s, and where somehow this c plus minus theta s are again something which is written as before, but with a different parametric circuit. And the parametric circuit basically looks like this. So you have something, so you have again the W, so the one which is independent on theta. Then you have the exponential of this gate. Then you have something which is like a standard one, so plus minus I pi by 4, and then you have something else. And then we have the V's again, the operator V, and then all 0. Okay, so it looks a bit more complicated, and then you see, okay, so why this is interesting again? So we are turning a derivative into an integral, but the nice point of this identity is that now you can estimate the gradient by mixing measurements on a quantum computer and stochastic strategies. So what you do is that you replace this integral with like a Monte Carlo approach. So basically you sample S from the uniform distribution. Then once you have sampled S from the uniform distribution, then you can compute this circuit. It's based with this, is made of the same gates you have used before. And once you have this circuit, you can find an estimator of the gradient. Okay, is this clear? Or? Sure?
So, unlike the previous one, this would be a biased estimate?
No, this is still unbiased. This is still an unbiased estimator of the gradient. Yeah, that's an important point. Yes. So the reason why, I mean, since there is this external stochastic sampling of another variable, so that's why somehow this is called the stochastic parameter shift rule. And it is used basically for generic Hamiltonians, so provided that your Hamiltonian can be written as qubits. Now, I mean, if you have like, so I don't know if you already know Penny Lane, but in Penny Lane website there are lots of great tutorials, and there is also one tutorial here about the stochastic parameter shift rule and many other things about variational stuff. And here, for instance, you can show some tutorial and also some code to play with this approach here. Okay, so I recommend for you to have a look at this website for some coding and examples. Now, so what I said, so by mixing the stochastic parameter shift rule, so one can find derivatives with respect to, let's say, generic multi-qubit gates, but you need to have qubits. And so, for instance, transmon systems sometimes can be better approximated via Q-treats or QDITs with other levels, and in that case, somehow this derivation doesn't apply, but there is a generalization. Let's say, and the generalization for QDITs, there are many papers. QDITs. I mean, the one I'm referring to is this one here, so which is archive 2107.12390. And somehow in this paper, they show that the derivative of the cost function can be written as a sum over with mu equal to 1. I just write the result, okay? I won't perform the derivation. Chu r, which c chu mu minus 1 pi divided by chu r. And then there is some complicated part, which is mu minus 1, which is 4r sinus square chu mu minus 1 divided by 4r pi. Okay, I mean, it's a complicated one, but the point is that, so this derivative, so I didn't tell you, so this r here is basically, is the number of frequencies, and it's somehow connected to the number of different eigenvalues, equidistant eigenvalues of the gate G. So this still applies when you have like gates like E, theta, G, and in this G you have like R different equidistant eigenvalues. So for qubits, the R was just 2, and you find the parameter shift rule as a sum of 2 different evaluation of the function. So here you see that somehow is a bit more complicated, and but I just wanted to mention this result because I mean, it might be useful for people doing field theory, where in general you might not have qubits. For instance, you might have representations of more general groups like SU3, F4, I don't know, whatever, right? Okay, so I'm not an expert on that part. But I mean, and so what I'm saying is that, so even when you have, let's say, more general groups, so instead of Pauli matrices, you might have Gell-Mann matrices or whatever, you can still apply parameter shift rules. And this result can be also, of course, combined with the stochastic parameter shift rule to find derivatives with respect to generic evolution beyond qubits. Okay, and again, if you're interested, so there are some codes as well in Penny Lane, which is this one about generalized parameter shift rules when you have this more generic treatment. Okay. Questions so far? Okay, so let's try to make a summary of what we have done. So the summary is that, so you can write the derivative of a cost function evaluated on as an expectation value, of some unbiased estimator of the gradient. And this expectation value can be over, for instance, all the measurement shots, or over other, let's say, stochastic sampling, like in the stochastic parameter shift rule. Okay, but the point is that this is an unbiased estimator, and right. Okay, so the point is that we cannot obtain the exact gradient in the hardware, but because we are using a finite number of measurements, but we can obtain a statistical estimator of the gradient. And so, and the best way we can use the statistical estimator of the gradient is to use what is called the stochastic gradient descent. So to update the parameters, so the parameters are updated. So n here is the iteration. So one use the old parameters minus gamma, which is like a learning rate, and then g, which is our estimator of the gradient. So let's say that your cost function, your 3D cost function looks like this. Okay, this is my best drawing of a hill. Okay, and you want to go downhill, so you start from here, and let's say the exact gradient is this one. So what the stochastic gradient descent is doing is that somehow it fluctuates. Okay, so it's not following the right path, but on average it is going into the right direction. Okay, and the reason why it goes into the right direction is because the estimator of the gradient is unbiased. So if the estimator is biased, then somehow you don't have this property. But the stochastic gradient descent has been studied a lot in let's say, for instance, in the machine learning literature, because it's used a lot in that kind of literature. And so there are many convergence theorems that basically tells you that provided that G is an unbiased estimator of the gradient, so stochastic gradient descent converges to the local optimum. I mean, some people also claim something about the global optimum, but that's, I mean, not very solid, okay? Because they say fluctuations, they can escape local traps, but I mean, that's not particularly, I mean, I haven't found a convincing proof. I mean, if you know that, if you know some convincing proof, let me know. Right, and and if you also read that kind of literature, you will also see how many steps are needed to achieve this, to find, let's say, convergence. And so by reading the machine learning literature, so you realize that basically the difference of the cost function at iteration n minus the cost function for the optimal parameter, theta. So theta opt is the optimal parameter. So the one that achieved the local minimum. So this can be somehow, this goes like basically the square root of the variance, not the variance, well, I mean, kind of a variance of the gradient estimator divided by the number of iterations. Okay, so this converges a bit slowly because it's like a square root of the number of iterations, but this converges, okay? So it goes to 0 as n goes to infinity. And so the number of steps, so the convergence time, so the number of iterations, you see that basically goes like the variance of this gradient estimator. And so something which is, I think, is quite, so this is some results from machine learning literature, okay? So what I find interesting is that also this EG square can be bounded by the quantum Fisher information. So you have seen the quantum Fisher information yesterday, because the quantum Fisher information can also be used to define a more refined version of the gradient descent, which is the natural gradient. But it can also be used to somehow bound the convergence time of, let's say, even vanilla stochastic gradient descent. So this is just the Fisher information matrix. No, wrong bracket notation. Okay, and somehow, if you're interested in this connection, I mean, you can also check these papers here. Which is by Gentini and others like me. But I mean, there is also another paper where they have also shown that somehow the quantum Fisher information also measures the expressivity of parametric quantum circuits. So QFI measures the expressivity of psi of theta. So if this is somehow your Hilbert space, somehow the quantum Fisher information also tells you what kind of path you are exploring in the Hilbert space. In the Hilbert space, yes. Mm-hmm. Is the local optimum. Mm-hmm. Yes. So the question was, sorry. Yes. Yeah. So the question from the class was, So whether this C opt is the optimal, is the global optimum. This is not. This is the local optimum. Thank you. Right. So this was an important point. Right. So so the QFI, so the quantum Fisher information, has been shown to measure also the expressivity of a quantum circuit. So how much you are traveling in the Hilbert space, and basically, so you can also see the derivation in this paper here, which is by Haug and others, which is 2102.01659. Okay. So somehow larger QFI means that somehow your circuit is more expressive. But larger QFI means also that somehow the convergence, so the number of iterations, is larger. Okay, so there is a, so that's the reason why there is a trade-off between expressibility and what is called the trainability. So like how we can optimize of these circuits, of these parametric quantum circuits. Okay. Right, because I mean, if the circuit is highly expressible, then convergence is might be slower. Thank you. Peter. So Q5 is a matrix. Do you take the norm? Okay. No, I think you don't take the norm. I think it was made with the diagonal elements of the QFI, as far as I remember, or some. I mean, QFI is a matrix. That's a good point. That's for sure. I don't remember. I mean, exactly. So here in the, how do you say? So here, basically, you can use the largest eigenvalue of the QFI matrix to bound this quantity. I skipped all these mathematical details, right? And here, to measure the expressivity, I think it was a function of the diagonal elements, as far as I remember, or of the eigenvalues. I mean, I don't remember exactly the expression, but it's a function of the QFI. Yes. Okay, and I mean, this trade-off between expressibility and trainability can also be defined by using, let's say, how do you say, Barren Plateau, but I won't discuss that part. Okay, you can find some details more about that part in the review, which is this review here. So the same already mentioned by Peter yesterday. Right. Okay, so another common problem, and then this part that's done with the gradients, is that NISQ hardware in NISQ hardware we have noisy gates. So noisy gates means that somehow these noisy gates may introduce a bias in the estimation of the gradient, and that's bad because once you have a bias in the estimation of the gradients, then somehow this was again the true gradient. But if you do stochastic gradient descent with a bias, then somehow you can do like this. So you don't follow the right path. And so this is a problem. So noise typically introduces a bias. So noise but noise also reduces it also reduces the quantum Fisher information. This is not an implication, it's just a part. Okay, so once you have noise, somehow convergences might be quicker, but towards the wrong point. Okay, and so in general, so we need to be careful in the way we handle the outcomes from a noisy quantum device. So one should use mitigation strategies also to avoid all of these problems here. Right. So other questions? Okay. So if not, let me jump to another part of my lecture, which is basically, so I don't think, I mean, I was going slower than expected, so I don't think I have time also to show you the applications. So let me jump to the part about Barren Plateau. Yeah, I think yeah, half an hour. Okay. So let's see where Sure.
Balance in days, but maybe you have like a little variation, even if you get to the point, and to a case that you don't have that much variation, but you don't get that far, maybe what you want to get to, so you don't have a big bias, and maybe it's more convenient than the other, but maybe.
I mean, yes. So the question was that. So how do you balance whether you have a big bias, as far as I remember, but so I don't know if I understand correctly the question. So if you have like a big bias, so normally these techniques are based on some bounds. Okay, so they are not exact results. They tell you, I mean, this is in the worst case, things go like this. But in the numerics, so what you can do is just try and see what happens. So I think there is no general solution to your question. Okay, so it depends on case by case, and yeah. Sorry, it was a very vague answer, but yeah, it's difficult to answer. Let's say, questions when you're dealing with stochastic outcomes and you don't know whether this is biased, so you don't know where you're going. So I think the trick is to make it less biased. I think is a very naive answer, right? No, it's not a naive question. That was a very nice question. Thank you. Right. Okay. So okay. So now let's go to the second part, which is the discussion about Barren Plateau. What I have here? Barren. I never remember how it's written in English, because I mean it looks like French. But perhaps there is an E or there is no E. I mean I never remember how to write Plateau. Anyway, now the question is now, how big is the gradient? Okay, so that's the most important question here. So to successfully train a model, so the gradient has to be suitably large, but we will see it somehow that using random initialization of the parameter, so we may end up into a region of the parameter space which is very flat. So very flat means that the gradients are very small, and so you never get too far from the initial point, and that somehow it's a problem. So let's try to understand this the occurrence of Barren Plateau with more details. And so we will use again the same decomposition that we used before. So somehow we say that psi theta can be written as a, let's say, a W, E I theta j Hj. So these are units. So this W and V basically are independent on theta j, but possibly dependent on all the other thetas, and then apply to 0. Okay. Now, and again, the cost function for us is the usual one. So we are basically taking an expectation value with respect to this to an operator theta, and so one can show, and here we are considering the simplest case. Okay, so where again the standard parameter shift rules apply, but I mean everything can be generalized. So so one can basically show, using the usual tricks of exponentiating polymatrices, that the derivative of C with respect to theta j can be written as a, let's say, different coefficients, where you have sinus to theta j plus something else, which is the cosinus theta j. I mean, this is again can be obtained in the proof of the parameter shift rule. And so if you now consider an average, so what happens on average? Because somehow your theta j are let's say initially you don't know how to choose the parameters. So suppose that somehow you're considering an average. So if you do the average over all the theta j of this d c d theta j, so and you have like you're doing a uniform average like between minus pi and pi of let's say this quantity here. Okay, then you realize that basically because of the integral of the sinus and cosinus, here you get exactly 0. Okay, so the average is 0. Now this is not an issue because we never perform such averages. So we select one particular initial value of the gradient, and then we use it as a starting point to optimize everything else. And the point is that if you also compute the variance of this guy here, so the variance is quite large. So, I mean, that shows that somehow this is not an issue in general. However, once we calculated the averages, so we have also to take into account what happens here and here. So if we are initializing all the parameters at random, not just theta j, then also we have to see what happens in this part of the circuits like W and V. Now, so what may happen is that if the circuit is highly expressive, then basically changing theta I allows you to explore several points of the Hilbert space. So this is the Hilbert space. Okay. So if that's the case, then what we might find is that, so we might end up, so in what is called T-design, so possible. So what is a T-design? So T-design is like a concept from I don't know I'm not sure why it's called a design. I think it's like a term coming from computer science. But what's the design is like a collection of unitaries such that the average. So here we are considering an average over a continuous parameter of our circuit, but repeated like T times. That's the T in the T-design. And then applied onto some operator. So when we have a T-design, so this average here is basically close to the average over the uniform group. Okay, let's try to understand this a bit more. So O is an operator, like an observable. So U, theta is the parametric circuit that you're applying. And then you're taking averages. So you are averaging over all the possible initializations of your parameters. And so the claim is that so this average becomes similar to the average over the formal group. And where this guy here is what is called the Har measure. If you're not familiar with the Har measure, it's something from basically theory of groups, so Lie algebra. So this is a big claim, but let's assume that this is the case, and when we will see what kind of conclusions we get if this is true. Okay. Now, if this is true, then so let's try to expand. Let's try to expand. Let's say C of theta, which is again 0, 0. Then we have like this V dagger e to the minus I theta j aj. Then we have W dagger. Then we have A. Then we have W. Then we have again plus I theta j hj. And then we have like V. And then we have all the 0. Okay. Now, if you take the derivative of C theta with respect to theta j, then basically, so this can also be written as 0, 0, and then you have this V dagger, and then somehow the expression here can also be written as minus I H, and then you have minus I H theta J W dagger A W, and then you have again V 0, 0, 0. Okay, just double check this expression. It should be okay. Now, suppose that V is a true design. Okay, so suppose that somehow V satisfies this property here for t equal to 2. Now, if that's the case, then somehow the variance of the gradient, remember that the average is 0, so it can be written as average over dc d theta square, and so that's somehow why you need 2 here, and so if somehow if you call this thing here in the, so if you call this thing here an operator B, so one can show, I mean, I will skip all the calculation, but one can show that in this case, if this is like a true design, then this is actually close to an integral over dv, where we have 0, 0, v applied 2 times, and then we have like b applied 2 times, and then we have v applied 2 times, 0, 0, 0. Okay, so that's why somehow, and this is a dagger. So that's why somehow you get this this true design, and this is now an integral over a formal group. So you might say that this is quite complicated, and yes.
So how did we get 2 instead of a general T, or is that kind of something?
No, the ancilla. So the question is that how do you get the true ancilla? So the reason why you get true ancilla is that somehow you're taking, so you're taking the square here. So let me write this maybe in a different way, so then it's clearer. So this can also be written as 0, 0, and then V, B, V dagger, B, V, 0, 0, but square. Okay? So this, the reason why this is square, so you're taking 2 copies of the B dagger and 2 copies of D. So they can be arranged in a form like this, right? And now, so the point is that even though somehow these integrals are a bit technical, so mathematicians found a way of computing these integrals analytically. And so, I mean, I won't do the calculation, but so if you're interested in the calculation, let's see, so you should see McLean et al., which is like a NatCom paper from 2018. So it's basically this paper here. Let me see where I have it. Not here, not this one. No, yeah, this one here. Okay, so this is the paper. So here you can find all the derivation about this result. So it's Barren Plateau in quantum neural network training landscapes. But the result from this paper is that somehow, so the variance of dc by d theta j is something which is of the order of like a polynomial of 1 over 2 to the n. Okay, where n is the number of qubits. So you might realize that somehow this is bad, because it means that somehow the variance goes to 0 as a number of as n goes to infinity, and it goes quite quickly. So it goes exponentially, so more than exponentially to 0, right? so the fact that somehow the variance goes to 0 is something which physicists in statistical physics call self-averaging. That's somehow the notation used in physics, while mathematicians call this phenomenon like concentration of measure. But I mean, in spite of the names, so what does it mean? So it means that basically since basically the variance is 0, a single sample is asymptotically close to its average. Okay? So single sample close to average. But the average is 0, right? So since the average is 0, so it means that somehow asymptotically, so as the number of qubits increases, so if this assumption is true, so that somehow the average over parametric quantum circuits approximate a true design, then so with high probability, the gradient of the cost function is 0. So with high probability, is exponentially small. Okay. Right, and this problem affects, let's say, parametric quantum circuits, the trainability of parametric quantum circuits, and why so? So, for instance, so this has been discussed in this paper in the review by Cerezo. For instance, there is a nice plot here. Where is that? So it's basically yeah. So what happens is that, so this is like a cost function landscape for 2 parameters. So what happens is that, so when you increase the number of qubits, well, first of all, you see from the left here, so in A, that the variance decreases exponentially. So the numerics actually agrees with the prediction from group theory. And what happens is that somehow the parameter landscapes, as the qubit increases, becomes more like this here. So more like, so the minimum of the cost function looks like what they say a narrow gorge, okay? And this is a problem because if you have like a narrow gorge like this and you're doing gradient descent, so for instance, suppose that this is your cost function, but you are here and you're doing gradient descent. So gradient descent, I mean, if the learning rate is large, then somehow you might pass through this gorge without even realizing that the minimum was there. So the step is too far. And somehow, because of the width of this part here decreases exponentially, then, I mean, it's quite likely that somehow you missed the right point. Okay? So this is a problem. And let's say, so so other forms of so this is, let's say, the standard way Barren Plateau appear in parametric quantum circuits, and other forms of Barren Plateau are due to poorly chosen cost functions. And for a discussion, I recommend basically this paper here. So Cerezo, which is called cost function dependent which is this other paper here. So it's another Nature communication from 2000, I think, no, 2021. And here they show that somehow if you have like a global cost function, no matter the circuit depth, so no matter whether the circuit depth is ρ1, logarithmic in the number of qubits or anything, so you always get Barren Plateau. While, for instance, if you have local cost functions, and we like that if you want to simulate, for instance, VQE, because you have like local Hamiltonians. So if you have local Hamiltonians, then somehow things are trainable, provided that somehow the depth of the circuit is not too big. Okay, so if the circuit is too big, is too deep, then you have lots of parameters, so you are in this over-parameterized regime, then somehow you might, with high probability, end up in a Barren plateau. But if the circuit is relatively shallow, then everything is kind of fine. Okay, and there are also some mitigation strategies to avoid Barren plateau. Now, I don't have time to say that, but let's say there are some mitigation strategies. For instance, for, let's say, the problem is that random initialization, that's also the problem. So if you have like more careful initializations of the circuit, then somehow things get better, but let's say formal proofs are just as a function of the depth of the circuit. Thank you. The impact of noise on the occurrence of Barren plateau. Yes, there is another paper by the same group, Los Alamos group, which basically say that noise also gives rise to Barren plateau. I mean, noise makes the cost function flat, right? And flat cost function means, again, like a Barren plateau. So also noise affects Barren plateau, yes. And there is a paper also by the same group. So I mean, you can also, I don't remember all the details of the paper, but you can also check that one there. Okay, so questions so far? Yes?
You mentioned how the idea is that if you have enough expressibility, then you will randomly sample from the group. Is this something you can do? Like if the quantum Fisher information goes up, then you will approach the design or something like that?
That's a good question, actually. Yes. So the question is that whether, so using the Fisher information, one can understand whether we get a true design or not. And the answer is that I don't know. I don't know, but that's a very good question. So it might be. So it might be, but I don't know the connection between the Fisher information and the appearance of Barren plateau. Yeah, but it's a good question. Yes. Question in the chat. So is the circuit depth that is trainable sufficient for us? What can we say about the problem we can solve with such circuit? Yeah, I mean, this is a very, very important question. So thanks, Peter. I mean, this is a problem in general, okay? Because, well, so this is in general a problem because when you have something like this, so short depth circuit, I mean, those are also the circuit for which you can use, for instance, like tensor networks for finding good approximations of the dynamics. And then you say, okay, so then if I use tensor networks, so why do I need a quantum computer? I mean, as far as I know, there is no general consensus on the literature about this issue. So there are also other strategies to mitigate, as I said, Barren plateau, even for longer circuits. But these are more like empirical, okay? So they work in practice, but there is no formal proof. So if you want to stick to formal proofs, then somehow that's the outcome. And yes, so we don't know whether we can achieve quantum advantage here. So, but this, I mean, this is a question which is, I would say, not well answered in the literature, as far as I know. Yeah. Other questions?
It's always been paper that people want more specific on the circuit, expressive, but I'm wondering because in deeper you want, right, is to reduce the specific.
Sorry, so the last part, what do you say?
So, I mean, I don't see why people want to have really explicit circuits, since we know that on passive side it is a problem, and it's why we have all these biases.
Yeah, okay, so the question, as far as I understand, is that, so why people then want more expressive circuits, while, so more, I think people want carefully designed circuits, okay? So that's, I would say, the answer. So if you have like a problem-dependent circuit, that's better. So if you're able to design from first principle a circuit which works well for your problem, then that's better. And as an example, if you know QAOA, or this, what Peter mentioned yesterday, this Hamiltonian variational ansatz, so those are ansatz which are kind of tailored to a particular problem or to a particular hardware. They're kind of, so you might guess that somehow your optimal circuit has some structure because of either, I don't know, using whatever, as in QAOA, that was the adiabatic theorem, or you have some physics inspiration of why that circuit is good for you, or coupled clusters for people doing simulation of chemistry. So those are, let's say, physics inspired circuits, which are expected to be good for a certain problem. I think so if one has, let's say, an intuition to use those kind of circuits, I mean, those are the best strategies. If you on the other hand, you don't have any intuition at all, and you want to, let's say, study things which are the most general circuits, like something with a lot of parameter, then I would say expressibility is a problem, because it's not like in neural networks where this over-parameterized stuff makes things better. So here it seems that it's worse. Yes.
So if you take, for instance, like a paper about this dimension of networks, where they show that higher dimension. So I mean, it's good, right, on the first read, but yeah, if you can put the accuracy of 3.5 possible networks, which have like low dimension, which are much more.
Yes, I mean, thanks for the question. So the question was that basically also in quantum neural networks, there is this notion of the effective dimension, which again depends on Fisher information. And I mean, if you actually, it's a bit even more tricky than that, because so if you're interested in machine learning applications, then somehow when this effective dimension is large, so the circuit becomes highly expressive. So then what happens is that generalization is bad. Okay, because it's like overfitting. So you have too many parameters, and that's another issue, which is not related to this simulation stuff, but that's another issue for machine learning applications. Right. Did I answer to you? I mean, I want to say something more, but now I forgot. I mean, did I answer your question, or?
Yeah, I mean, well, just wondering how good this metric, and this metric is. It's not the more definitely how the best you are.
No, but I mean, there are even without studying the Fisher information. So we have also, I mean, I have also worked on this problem. So there are also information theoretic quantities to bound the expressivity of circuits. So we have also a paper with Jason, which is sitting on the back, about using mutual information to quantify the generalization in quantum machine learning, and that tells you exactly the same thing. So that the bigger is your space, the more you lose generalization abilities of this quantum neural networks. So there are not just the Fisher information, but let's say there are several, let's say, similar approaches that basically tells you the same thing. So if you have highly expressive circuits, then I mean they might be bad for trainability and generalization. Okay, thanks. So there are another question from Peter. What's the origin of the distance with respect to over-parameterization between parameterized quantum circuits and neural networks? That's a good question, actually. So as far as I know, so neural networks are good I mean, they're good for on technical reasons because you use like back propagation to efficiently compute gradients, and that's good. But neural networks are good because you use gradient descent. So that's somehow the important part. So neural networks are good when trained with gradient descent. And there is something which is called the lazy training, which basically tells you that somehow, since you are in this over-parameterized regime, so you have an infinite amount of local optimum, or let's say pretty good optimum. And because you have so many parameters, even if you just look at the neighborhood of the starting point, it's quite likely that you will find a pretty good optimum for the neural network. And this is somehow the idea of lazy training. And of course, there are also quantum versions of that. Yeah, and so it's an important question. I think there is no conclusive. I mean, I've seen some papers about quantum lazy training, some recent ones, but I'm not sure if there is a solution about your question in the literature. Yeah. And also, I mean, as a personal point, this is more like my personal view. So I don't know if it makes sense, the over-parameterized regime in quantum systems, because over-parameterization means that somehow we have pretty deep circuits. And I mean, clearly that's not something that can be used in NISQ devices. And if you have something which is not NISQ, then I mean, then why would you want to use like variational approaches? I mean, you can just use like Hamiltonian simulation methods, like the ones mentioned in Sohaib lecture for optimization, and also for machine learning. You have like algorithms like HHL, support vector machines. So all these things that can be done in fault tolerant quantum computers, and that cannot be done nowadays. So yeah, so personally, I don't think that the over-parameterized regime is so interested in quantum circuits, but that's just my personal view. Yes?
Can you get to the over-parameterized regime by considering away wide but shallow quantum circuits?
Sorry, I didn't get that.
Can we go to the over-parameterized regime by taking a wide but
yes, so yes. I just repeat the question is whether we can go to the over-parameterized regime with wide neural networks, and I mean that's a good point. That's a valid point, and this is something that we also asked ourselves with Giacomo, another speaker here. So it's definitely some possibility, and people in classical neural networks have done exactly that. But there is no conclusive answer. So these are all research questions. And another point is that if you just go wide but shallow, then again you can use tensor networks, right? To simulate the dynamics. So if you go wide but shallow, then why do you need a quantum computer? Yes?
You could go like instead of being constant shallow to log shallow, maybe there's like an intermediate.
Yeah. I mean, yes, you can play. I agree. So the question is that you can play with maybe not super shallow, but you can do some, let's say, trade-off. I mean, sure, these are all very important points. But as far, I mean, I haven't seen any solution to that point in the literature. There are some preliminary results, but I don't think there is a conclusive answer. Right. Other questions? So lots of questions. I mean, I'm happy with that, but I cannot. So my time is over. So it means I cannot do the application part. So you have already seen some applications with Peter about ground states and dynamics. So I wanted also to do an application for simulating low energy. So for finding low energy effective Hamiltonians on variationally. I don't have time for that. So if you're interested in this topic, just, I mean, I'm around. So just ask me about that later. Okay. So with this, I say I can conclude. All right. So thank you.